Last time we started section 11.1 and introduced some basic ideas that we have about geometry. And we had left off on talking about our two-dimensional base idea, which is the plane. A plane indicates a surface, but not a thickness. So if we're given three non-collinear points, right, 3 points that don't all lie on one line, there's exactly one plane that contains all three of these points. We name planes by either the 3 points on the plane or by a Greek letter like alpha, beta, or gamma. Okay? So I want you to sort of imagine in our classroom, because it's the easiest, I think, to visualize if I actually have you look at very specific places in the room. So we will use this top corner over here by the door. Okay? You can imagine there being sort of a location, a point there. We'll use the corner over there by the window. And then you can use down here the corner on the floor, or any of the corners or any of the points on the floor. So any of those, if you take those 3 points that you've just imagined, there's exactly one plane through that point, and it's the wall behind me, right? No other plane will go through all 3 of those points. Now you'll notice in that first part of the definition where it says they have to be non-collinear for this to be a true statement. So imagine again if you had the 2 corners of the room, but you had a point that was along the wall and the ceiling on that same line, right? There were 3 collinear points. You would actually have the plane behind me. You would also have the plane that's the ceiling, right? That'd be 2. And there'd be infinitely many others as well. We just don't have a visual in our classroom to sort of say, and look at this piece too. But there'd be lots of planes going through those 3 points. But if they're non-collinear, that's not a true statement. All right, so here's a picture of that same kind of a thing, a classroom, if you will. I know it doesn't draw, it's not drawn on your paper, is it? All right, so you guys can sketch that in. If collinear means that there are points that are on the same line. Coplanar means points that are on the same plane. And then, of course, non-coplanar would be points that cannot lie on the same plane. Not only do we have coplanar points, namely points that are in the same plane, we also have coplanar lines, which are lines that lie in the same plane. Yes, Emily.
Between the K and the M and L?
Yes.
Okay.
Yeah, it's a little fuzzy, hard to read on there, but it is an L. Or if there's, no, can't be fixed. Okay, so thinking about this picture, you can imagine the blue piece is kind of like the floor, and this would be sort of like my wall over by my door, and this would be the wall that we're up against on the projector wall itself, right? So we're going to use some of these points with this imagery to fill in lines and points and so forth that are coplanar and not coplanar using these descriptions. So some of the points that are coplanar, or an example of points that are coplanar, would be something like, I'll just write it over here, A, C, and D. So they're all along the same plane that's the blue plane, alpha. Now, I don't have a lot of extra points actually listed on my description here, but it's actually true that anytime I take 3 points, there has to be a plane that lies within, they have to all lie on the same plane. But once I extend that definition to having 4 points, it doesn't have to be true any longer. Now, if there were some additional point down here, in the middle of the blue plane, that white dot that I just made, that would also be coplanar with the ones that I already created, right? it would. But if I consider instead the point B up here, it is not coplanar with the other 3 points. Now, B and A and C are all coplanar and they lie in plane beta. And B and A and D are all coplanar and they lie in plane gamma. But all 4 of those points taken at the same time don't all have a plane that they all lie in. So that's the same. So an example of non-coplanar points would be, for our picture here, all of these, A, B, C, and D. And then coplanar lines that lie in the same plane. You can see some rays emanating down there, right? K, L, M, all those appear to be rays going out from point A. They actually are lines if they continued through A to the other direction. There's only so much you can draw on a picture before it starts looking messy, so you'll see partial pictures drawn quite frequently. But all of these lines, line K, line L, line M, are all coplanar. They all lie in that blue plane. In addition, you could even say that line AC lies in that plane, and line AD lies in that plane too. So those would be some examples of coplanar lines for this image. Now, if 2 lines are not coplanar, they have another name, and they're called skew lines. So skew lines are 2 lines that don't lie in the same plane. So let me give you a visual example again, classroom-wise, and I'll write this one in. If you take the line along the front ceiling, the one I told you about before, behind me, and the line along the side with the door. These are very technical descriptions, you can tell. So I got this line up here behind me, right along the ceiling, and I've got the line over here along the door. They don't lie in the same plane. There's no plane that would connect both those lines or have both those lines in it. It's not possible. Now, anytime 2 lines intersect, they are in the same plane. So imagine the line along the top of the ceiling and the line over here that goes from the bottom corner to the top corner of our room. They intersect in the top corner. They're in the plane that's actually behind me against the wall. So they do intersect. They have to lie in some plane in common. It wouldn't have to be the wall behind me. It just happens to be from my example. Now, if you have 2 coplanar lines that don't intersect, like I just described one that did intersect, but you have 2 coplanar lines that don't intersect, then they're actually parallel. So, and again, we'll write an example down with a visual for our classroom. Again, our line along the ceiling, I'll call it the front ceiling again. And the line along, and we'll just go with the back ceiling. So the line up here along my front ceiling, the line along the back ceiling, I think you could probably very visually see those are parallel lines. They don't intersect, and they're also in the same plane. See, the other 2 didn't intersect. The skew ones either, they didn't intersect, right? The one along the floor over here and the one along, so they didn't intersect, but they aren't in the same plane. That's why they're not considered parallel. All right? Now, a couple of questions to consider. Can skew lines have a point in common. Why or why not? Nope. Why not? Yeah, because intersecting so if they have a point in common, they're intersecting. So intersecting lines lie in the same plane. Some plane, right? They lie in the same plane. And if they lie in the same plane, they're not skew. Can skew lines be parallel? Go back over here to definition. How come? Say it a little bit louder.
Because they'd be on the same plane.
So it's no, because they would be. Hang on, let me see how I'm reading. In the same plane. Right? Parallel lines have to lie in the same plane. Skew lines can't. So skew lines are not coplanar, parallel lines are. You can't be both at the same time. You either are or you aren't. All right, so we're going to imagine some different objects intersecting and kind of figure out how they intersect. What does it look like when they do? So if we have two points are in a plane, the line containing them is where? What do you think you might be able to imagine or describe that as? If you're able to draw 2 points in the same plane, what can you tell me about the line that connects those 2 points? Don't overthink this, it's not hard. Okay. It's in the plane. Told you it's not hard. Now you guys are laughing at yourselves, right? Yeah, if you have 2 points in the plane and you can connect the 2 points in the plane, then the line that connects them is going to be in the plane. Now, the next 3 are a little bit more oddly worded, I kind of feel like. The first one was a little bit, but if you have a line, okay, so imagine a line. Maybe you want to imagine the ceiling line behind me since we keep talking about it. And you have a point that's not on that line. What will those create if you sort of attach them all together, connect them all together? It will create a plane. It will determine a plane anyway. Yeah, create's maybe not my best word, but determine. It will determine a plane. So again, imagine like my ceiling line, and then just take any point on the board, like the chalkboard. Well, that point on the chalkboard, that line at the top of the room, create or determine the plane that is the wall behind me. So these determine a plane. What if you have 2 different parallel lines? Parallel lines, what will those determine? A plane, you're right. They'll determine a plane. And again, you can take the same 2 parallel lines we talked about before. Take the one that's along the top of the classroom over here behind me and the one that's on the top of the classroom behind you. They form the plane that is our ceiling. Now, a little bit less obvious might be this one. So imagine the line that's along the ceiling behind me and the line that's on the floor behind you guys. Okay? Now, that's not any of our walls or our ceilings in the room, but can you imagine taking a sheet of paper at an angle and going through the top corner behind me and the bottom corner behind you? Yeah, it would determine a plane as well. So it's not necessarily that it is created in a physical sense, but it would determine it in sort of a spatial sense. We can see how that would be pieced together. So it also forms a plane. What about if you have two intersecting lines? They will determine a plane as well, if you consider them in their entirety. They intersect in a point, obviously. But if you consider the two intersecting lines, so again, maybe you do the one behind me on the ceiling, and you do the one on the ceiling over here by the door. They're going to intersect in the top corner, and they both lie in the same plane, namely the plane that's the ceiling. So yeah, they determine a plane as well. All right, two planes. We haven't done two planes yet. We've talked about lines inside of planes, but we're actually going to take two planes now. There are only two options. They can either be parallel, think floor ceiling, parallel planes. They have no points in common, right? Or they can be intersecting. There are no choices that are different than that. All right, so the lines had three choices. They can be parallel, they can be intersecting, or they can be skew. Our planes don't have that ability. They're either parallel planes, ceiling, floor, or they're intersecting planes, ceiling, wall. So parallel would be like, actually I'll write you an example. And then intersecting would be ceiling, wall. And when they intersect in a line. Sorry, I should have said that as well. That's part of the definition. So again, if I did my ceiling and my wall, my ceiling, and then we'll do the wall on the outside of our classroom over here, they would actually intersect in the line that goes along the ceiling at the top of the room, but along the wall on the side of the room as well. They would intersect in a line. Now, when you take a line, that's when you take two planes and you kind of compare them, what's the relationship two planes can have. The next one is actually taking a line and comparing it to a plane. What are the different options? So, one option is that we actually have a line that's parallel to a plane. Parallel always means something doesn't intersect, right? It does. So these are no points in common. And a visual example of parallel line to a plane would be a ceiling and any of the lines on our floor. Okay, so we've got our ceiling, and then we've got all these infinitely many lines that are our floor. You can almost think about it like the threads in the carpet themselves as being lines. They never intersect the ceiling, and they never will. So those would be parallel to one another. The next one would be, there's two types of intersecting, I should say it that way. There's intersecting where it's contained inside of it, and there's intersecting where it sort of penetrates or crosses through it. So if you were taking a look at something contained inside of it, again, you can imagine our ceiling, and then you can take any one of these sort of metal strips that's inside of our ceiling, and that could be considered a line. Now, that's not the only lines, right? We've got strips going left and right, but you sort of have like ones that you can imagine going diagonal if I wanted to do that too. So there's infinitely many lines within my ceiling, but that would be one way to describe this particular option. It's inside of the plane you already started with. So we can do the ceiling as our plane and a line within the ceiling, or along the ceiling if you prefer. And the other option is that it isn't actually one of these lines in the ceiling, it just sort of like pokes through the ceiling, right? So again, you could imagine the ceiling, and then if you take this line that goes up my corner all the way to the top, right along the two walls over here, it would intersect the ceiling as well, but only in that one specific corner. It wouldn't be contained inside of the ceiling, but it would cross through the ceiling. So that would be my ceiling. And really any line along the wall. Okay, a few more relationship kind of descriptions to look at. Perpendicular lines. Perpendicular lines are lines that form right angles when they intersect. And we write it with the line, right, L and L, like L and K. And perpendicular notation looks like an upside down T, capital T. That's perpendicular. You probably recognize that from before. A line can be perpendicular to a plane as well, not just necessarily to another line. And it's perpendicular to a plane if it's perpendicular to every line inside of the plane. And this is the image that I sort of created a moment ago when I referenced a ceiling with the line along the corner. So my line along my corner over here would be perpendicular to the ceiling. And the reason it would is because it's going to be perpendicular to this wall. Good gracious. Let's try that again. All right, so it's going to be perpendicular. This is my line. It's going to be perpendicular to the ceiling along this wall, and it's going to be perpendicular to ceiling along this wall. And you can imagine all the other lines that would emanate from there, it would also be perpendicular to them. It would form right angles. If you have two planes that are perpendicular, this happens if any angle formed by a line in one plane and a line in the other plane is a right angle. So you could actually imagine, again, my ceiling. With, at least in this room, one of the walls. Now, that's not true for every ceiling and every wall. We have a room in our home. We have a second floor, but you can actually see the roof line built into it. So our walls are not, or I should say our ceilings are not actually horizontal to the floor. They're at an angle. So it wouldn't work in my description of my upstairs of my home, but it works in this room, right? You can see that the horizontal, the flat ceiling, because it's horizontal, and then our walls are perpendicular. So these would actually be perpendicular planes. All right, so let's move a little bit away from that, and we're going to talk about angles for a bit. First, we're going to break down the anatomy of an angle. An angle is formed when two rays share an end point. The rays are called the sides of the angle, and the shared end point is called the vertex. You can see the diagram where I've labeled side, I've labeled vertex. The blue rays are forming the angle. The shaded part is referenced in that sort of beigey color is actually the interior of the angle. It's the part of the plane between the two sides. Now, one could argue that this piece out here is also between the two sides, but it's the bigger of the two options, so we would call that the exterior, just so you know. The interior would be the smaller portion. In this picture, it's the part that's shaded in. Sorry, I know you're drawing pictures. Some of the pictures later on will actually be already in the notes. You won't have to draw them. But sometimes it's really hard to get the pictures to paste in, so. Am I good to switch screens? Yeah? Okay. A bit more about angles. Angles can be named in a number of different ways. They could be named by a number, angle 1, angle 2, angle 3. It would be labeled that way, but they could be named by a number. They could be named by a Greek letter. That's what you see in this picture, alpha and beta. Those are angles. Or they could be referenced by the vertex of the angle, or 3 points along the angle itself. So on this one, for example, if I talked about angle P, it would be unclear what I meant. Do I mean this angle here? That's angle P, because P is the vertex. Or do I mean this angle here, because P is the vertex? Or do I mean this angle that's on the outside, because P is the vertex? So when it's unclear, we need more description. So we would either label it as angle, like let's say we're using this one right here to reference. We would use the letters Q and R as well, and we would list them, I'll use it here, as angle Q, P, R, or angle R, P, Q. So you're listing P in the middle. You're going around the angle. The P is in the middle because it's the vertex. So if you start with Q, you go Q, P, R. If you start with R, you go R, P, Q. And that distinguishes it from the other angle P's that are in the picture. Now, if you were looking at, just let me flip back real quick, but you don't need to write anything down. If you were looking at this one, there's absolutely no reason to call this angle ABC. It's not wrong, and you could, but angle B is plenty descriptive enough because there's only one image in this picture that makes sense to call angle B. That didn't happen over here. Two angles are called adjacent if they share a common side and a common vertex, but they do not share parts of their interior. In other words, they don't overlap. The interior pieces are not overlapping one another. So this image right here is actually an image of two adjacent angles. Angle alpha and angle beta are adjacent. They share the vertex P. They share the ray side PR. They share that ray. And their interiors do not overlap. Right? They don't do like this and blend together. That's not what's happening. Now, as far as what we're going to work with in this class, and what you most likely would see in the curriculum you would be teaching to children, the most common measure for an angle's opening is in degrees. Now, some of you are probably fully aware that that's not true when you get to different types of mathematics, and it's not. But for the level of mathematics for junior high and below, which is your certification sort of age grouped area, degrees are what you see used all the time. The notation for the degree is the little degree marker, a little circle that's sort of up in the air there. And a full rotation or a circle is 360 degrees. So 1 degree is actually 1/360th of a full rotation. You can almost kind of imagine it's the size that a day takes up of a whole year. It's not perfect, right, because we don't have 360 days in our year, but it's about the same idea. It's very small. 1 day out of the whole year is not very much. 1 degree is also not very much. We can break a degree down into smaller units, minutes and seconds, just like you can take your day and you can break it down into minutes and seconds, okay? So the way that we do that is, in fact, I think that's on my next slide. Oh, it's right here. I just didn't actually say it. Let me see it. So each degree can be broken down into 60 smaller parts called minutes, and then each minute can be broken down into 60 smaller parts called seconds. So the idea of the number 60. So we're going to do some examples of taking degrees and changing them into minutes and seconds, and then changing minutes and seconds back into degrees. So this would be an example of degrees. It is 32.46 degrees. Okay? It's kind of like when somebody asks you, how long is this class period? You probably don't tell them it's 5/6 of an hour. You could. It would be true, but it'd be sort of weird, right? We don't talk about it quite like that. You're more likely to tell them it's 50 minutes. Agreed? So that's the idea here, is that these decimals can be changed into degrees and minutes, and there are times when that makes more sense to do so when you're expressing them. So what we do is we take our 32 and we leave it. It's 32 degrees. right? It's like if you talk about an hour and a half, you don't change the hour into minutes, and we don't say an hour and a half. We usually don't say an hour and a half and talk about 90 minutes. That's not how we usually do it. We say an hour and a half, right? Well, the 32 stays. The 0.46, what happens is we take that 0.46 and we multiply it by 60. Because degrees, 0.46 degrees times 60 will give me minutes. So grab a calculator if you have it with you. I do hope you do. And find out for me what is 0.46 times 60. I'm going to put a plus sign in between these for now. Fabulous. 27.6. And we do minutes by like it looks like an accent or like an apostrophe or a accent mark. I don't care what you want to call it. They're all pretty much the same, but that's what it looks like, okay? That's minutes. You notice I still have a 0.6 though, right? So we're just going to do it again. So now I have the 32 degrees that stays the same. I have the 27 minutes that stays the same. And then I take that 0.6 and I multiply it again by 60, and that will turn my minutes into seconds. So what is 0.6 times 60? 36. And we do seconds by doing 2 of the accent marks. Almost looks like quotations now. Okay? So these are the different pieces. We don't usually have the final answer written with the pluses, though. Like that doesn't make any sense. The addition symbols, we would write them all right next to each other. This would be 32 degrees, 27 minutes, and 36 seconds. That would be the degree minutes seconds notation that corresponds to 32.46 degrees. So what I'd like for you to write next to this sort of as a reminder, when you go from degrees into degrees, minutes, seconds, you multiply. And truly, you're multiplying by 60. You might have to multiply by 60 twice. It might just be a whole number of minutes and then you're done, but it might not, like this one. So if you're going from degrees into degree minutes seconds and you multiply by 60, what happens if you do it the other way around? You're going to divide. You're right. So if we're going from degrees minutes seconds into degrees, we're going to divide by 60. So let me show you how that actually looks. Our 48 will stay the same, just like the 32 stayed the same on the previous problem. The 57 will get divided by 60. But indeed, the 36 will not just get divided by 60, it will get divided by 60 squared, because it's seconds. Just like we got the seconds on the previous problem by multiplying by 60 twice, we turn the seconds back into degrees by dividing by 60 twice. And if it bothers you to see the 60 squared written that way, that's really just 3,600. That's what we're really dividing by. Okay, so if you take your calculator, you'll take your 48. We have 57 over 60. So my 48 is still 48. I'm just separate them out just so you can see where the pieces are coming from. This piece in the middle is 0.95. And then we have 36 divided by 3,600. And we have 0.01. 0.01 back here at the end. If we add all those pieces together, we get 48.96 degrees. So the first computation thing we've done all day, right? Multiplying and dividing by 60. And your calculator can be helpful with that. All right. Our next problem is actually what we would do to take a value that is in degrees, minutes, and seconds and do some operation with them. You can do addition, you can do subtraction. I'm going to show you an example of subtraction. Addition works very similarly. And the idea is exactly what happens when you add and subtract with whole numbers. we borrow, we carry, we do those sorts of things. You just have to remember you're doing it with the idea that there's 60 minutes in an hour, in a degree, there's 60 seconds in a minute. So I'm going to line them up to start with as a reminder. There's 89 degrees, 37 minutes, and 24 seconds. And I subtract from that 48 degrees, 57 minutes, and 21 seconds. So typically, the standard operations for adding and subtracting have us start with the smallest unit, in this case the seconds. Now, if we were adding, we would add 24 and 21 together, and that'd be great, and we just move on. This one's subtraction, and we can actually do that subtraction, no problem. What's 24 minus 21? That's 3. So there's 3 seconds. So when the numerator, or not numerator, but when the value on top is bigger than the value on bottom, it just looks like subtracting whole numbers. It doesn't work quite like that for the 37 and the 57, right? I can't do 37 minus 57 and have a positive number to show for it. So what do I need to do? Well, we need to borrow. So what we're going to do is we're going to take our 89 degrees and we're going to borrow a degree, which means I'm going to be left with 88 degrees. Does that make sense so far? Excellent. But when I take a degree and I turn it into a minute, how many minutes does it become? 60. So I didn't borrow 10 like I do when I do this right in base 10 stuff, just our normal subtraction. I borrowed 60. And I borrowed 60 and I already had 37. So how many minutes do I now have? 97 minutes. Can I do 97 minutes minus 57 minutes now? Sure, no problem. What is 97 minus 57? 40. So that one was nice because I didn't even have to worry. The sevens just cancel. It's lovely kind of subtraction. If you had been encountering something like, let's say it said 95 minus 57, okay, if you want to just grab your calculator to do that subtraction. I'm far more concerned right here with your ability to add and subtract place value across, right? So like borrowing or carrying from minutes to seconds and things like that, okay? The last one is 88 degrees minus 48 degrees, and that gives me 40 degrees. So I have 40 degrees, 40 minutes, and 3 seconds. And there's the note on here. As long as your values for minutes and seconds are between 0 and 60, leaving answers in degree, minutes, seconds format is considered simplest form for your answers. All right, so a little bit more about angles. Some pictures for you to draw. There are 4 types of angles that your book mentions. The second one, the one's in the top right-hand corner, is called, well, sometimes isn't mentioned in books, I should say it that way. So the first one actually is an acute angle. The one right next to it, which is sometimes not considered an angle, is actually called a straight angle. And again, some resources, some books you might teach out of might not even mention it. The one underneath the acute angle is a right angle. And then the last one here is called an obtuse angle. Okay, if you've seen these angles before, shake your head. Yeah. So there's 4 types of angles. A circle is actually the set of all points in a plane that are the same distance. That distance is called the radius. From a single point, that point is called the center. And if you walked along the edge of the circle, that blue part right here, that would be called an arc. Lydia?
Could you go back really fast?
Mm-hmm. So an arc of a circle, you might kind of imagine it's like the crust on a pizza. That's the arc. Any part of a circle that you can draw without lifting your pencil. It's important to notice, because sometimes we don't think of it this way, the letter O, the center of the circle, is not a part of the circle. It determines the circle, right? It gives it sort of its shape or its distance or its size, but it is not part of the circle. The circle itself is just the outer edge. And a portion of that outer edge is an arc. So on this image, we have the center, not on the circle, but it's the center O. Also here you can see that we have the radius. The radius is OA as drawn, or you could call the radius OD. It's another radius in our picture. And we have several arcs. We actually have the arc BC. Arcs are drawn like a curved segment on the top, arc BC. We have the arc CA. We have the arc AD. And I'm going to put etc. because we're going to talk a little bit more about ways that we get arcs next. But those are three of the arcs in our circle. Each pair of points on the circle determines two arcs. The shorter arc is the minor arc. Sometimes it's labeled with only the end points. So for this picture here, AB, you don't need to draw the picture again. I just have it pictured on here again so I don't have to keep flipping my slides back and forth. But AB would be considered a minor arc. Okay, so it would be right here. The reality is, though, that A and B also determine another arc going the long way around, right? That's called a major arc. The major arc is always named by 3 points. So on this picture, that same arc AB, A and B are the end points, but the point that would be listed, at least here, that it also goes through would be D. So if I go around this direction, right, it would be ADB, and I would have the arc on top. So if there's only 2 points listed, it's the minor arc. If there's 3 points listed, it's typically the major arc that they're referring to. If you happen to have the major and the minor arcs and they're the same size, that's called a semicircle, right? It's halfway around. All right, one last thing to make a comment of, and then we're going to we'll stop and I'll tell you what's happening next. All right, a chord. A chord is a segment containing 2 points on the circle. If the chord runs through the center of the circle, it's called the diameter of the circle. So, for example, on this one, there would be a chord AC. Notice it's a flat segment. It is the segment AC, not the arc. So in our image over here, it's this right here, AC. But then if it actually goes through the center of the circle, we would have a diameter. In ours here, the diameter is AD. And it's this piece right here. Okay. So, we're not going to do the homework between now and Friday. You're welcome. That means you are going to have to do the homework over the weekend because then it'll be due Monday. So if you want to start it, you certainly could. However, the group work, please don't start it. We will do that in class next time. So what will happen next time in class is that we will move on to section 11.2 because we finished the notes, obviously, for your 11.1. So if you don't have 11.2 printed out, make sure you've got them printed out before you come. We'll start section 11.2 notes. And then you will split up into groups and you will work at the very end of class for about 10-15 minutes, something like that, on the group work from 11.1. Now, before you leave, I'm going to split you into groups so that you'll know who you're working with because we have just 2 minutes left.